These are the facts about space that will reshape how you see the universe. Space is not what most people imagine when they look up at the night sky, and the reality hiding beyond Earth's atmosphere contains phenomena so extreme they challenge human comprehension. The universe expands faster than light can travel. Right now, galaxies at the edge of what we can observe race away from us at speeds exceeding 186,000 miles per second, and space itself stretches between us and them at rates that make Einstein's cosmic speed limit irrelevant. The observable universe stretches 46 billion light-years in every direction, despite being only 13.8 billion years old. And this mathematical impossibility becomes possible only when you understand that the fabric of space-time itself expands independently of anything moving through it. When astronomers measure how fast distant galaxies recede from Earth, they use redshift, a phenomenon where light waves stretch as space expands between the source and observer. The farther away a galaxy sits, the more its light shifts toward the red end of the spectrum, and by measuring this shift, scientists calculate both distance and recession velocity. Galaxies 1 billion light-years away move away from us at roughly 14,000 miles per second, driven by cosmic expansion. Galaxies 2 billion light-years distant recede at 28,000 miles per second. This pattern continues linearly until you reach the edge of the observable universe, where galaxies flee at 3 times the speed of light. The Hubble constant quantifies expansion rate, currently measured at roughly 46 miles per second per million light-years. What this means in practical terms reshapes everything. Take a galaxy sitting 1 million light-years away, and space between us and that galaxy expands by 46 miles every single second. A galaxy 10 million light-years distant sees 460 miles of new space materialize between us each second. Scale that up to a galaxy 1 billion light-years away, and 46,000 miles of space appear between us every second, creating a recession velocity of 165 million miles per hour. The math becomes staggering when you calculate what happens at the cosmic horizon, the boundary of the observable universe sitting 46 billion light-years away. At that distance, space expands fast enough that light leaving those galaxies right now will never reach Earth, because the space between us grows faster than photons can cross it. Nothing breaks the light speed barrier by moving through space. Einstein's special relativity forbids any object with mass from reaching light speed, because accelerating toward that velocity requires infinite energy. The universe exploits a loophole though, because space-time itself expands without moving through anything, and general relativity places no speed limit on how fast the fabric of reality can stretch. Space carries galaxies along for the ride, and from the perspective of those distant galaxies, they sit perfectly still in their local reference frame while everything else rushes away from them. The expansion looks identical from every vantage point because space stretches uniformly in all directions. This creates the cosmic horizon, an event boundary beyond which we can never observe or reach anything regardless of technology. Light from galaxies past that boundary started its journey toward Earth billions of years ago, but expansion carried those galaxies away faster than their light could approach us, and the photons make no progress toward Earth despite traveling at maximum speed through space. They swim upstream against a current too powerful to overcome. Galaxies sitting just inside our cosmic horizon today will cross beyond it eventually, because acceleration continues, driven by dark energy that makes expansion speed up over time rather than slow down as gravity would prefer. The cosmic microwave background marks the farthest light humans will ever detect. This ancient radiation started its journey 13.8 billion years ago, when the universe was just 380,000 years old and hot enough that atoms could not yet form. Electrons bounced freely through the plasma, scattering photons in all directions, until temperatures dropped enough for electrons to bind into hydrogen atoms, and photons could finally travel unimpeded. That moment of first light stretched across the entire universe simultaneously, and the glow from that event reaches Earth today from all directions because we sit inside the expanding sphere of that ancient flash. The objects that emitted this light sit 46 billion light-years away now, because expansion carried them outward during the photon's journey toward us. Temperature measurements reveal another mind-bending fact about cosmic expansion. The universe cools as it grows, with the cosmic microwave background radiation currently registering 2.7 Kelvin. barely above absolute zero. When that radiation started its journey, the universe was roughly 3,000 Kelvin, hot enough to glow with visible light. Expansion stretched the wavelengths of those photons by a factor of 1/100, shifting visible light into microwaves and dropping the energy by the same proportion. This tells us the universe expanded 100 times larger during the photon's journey, transforming from a space roughly 42 million light-years across into today's observable cosmos, spanning 93 billion light-years in diameter. Dark energy drives acceleration, making expansion speed up rather than coast or slow down as matter's gravity tries to make it do. Scientists discovered this acceleration in 1998 when they measured distances to distant supernovae and found those stellar explosions appeared dimmer than expected, indicating space between Earth and those ancient stars had stretched more than predictions allowed. The universe expands 9% faster now than it did 7 billion years ago, and that acceleration continues increasing. Dark energy comprises 68% of all energy in the cosmos despite remaining completely mysterious. Scientists do not know what it is, where it comes from, or why it exists. They know only that it pushes space apart with a pressure that overpowers gravity's pull on cosmic scales. The implications ripple through everything. Galaxies beyond 4.5 billion light-years recede faster than light can cross the space between them and us right now, which means sending a signal to them today would fail because that signal would never arrive. Light from Earth would chase those galaxies forever without catching them, swimming against expansion's current. The boundary of reachability sits much closer than the boundary of observation. We can observe galaxies 30 billion light-years away because light they emitted long ago when they were closer has reached us, but we cannot send signals to their current location because expansion carries them away too fast. The universe we can interact with shrinks every day, even as the universe we can observe remains constant. Galaxies bound together by gravity resist expansion. The Milky Way and Andromeda galaxies sit just 2.5 million light-years apart, close enough that their mutual gravitational attraction overpowers cosmic expansion completely. Both galaxies approach each other at 250,000 miles per hour and will collide in roughly 4 billion years, merging into a single giant elliptical galaxy, sometimes nicknamed Milkomeda. This collision defies expansion because gravity dominates at close range. The local group containing the Milky Way, Andromeda, and about 80 smaller galaxies will remain bound together forever despite expansion pulling more distant structures away. The local group occupies 10 million light-years of space, and gravity within that volume wins the war against dark energy. Galaxy clusters also resist expansion for the same reason. The Virgo cluster contains roughly 2,000 galaxies packed into 15 million light-years of space, and gravity holds this structure together permanently. The Coma cluster spans 20 million light-years and contains thousands of galaxies, all gravitationally bound despite the universe's expansion trying to tear them apart. These clusters sit in space like islands resisting a tide, surrounded by the expanding ocean of space-time that sweeps everything else away. The boundary between bound and unbound structures sits around 350 million light-years today, the radius within which the local supercluster's gravity barely manages to slow expansion, even if it cannot stop it completely. Time itself warps in ways that shatter intuition. When you stand on Earth and look up at the sky, every second ticks forward at what feels like a constant rate, but that perception lies. Time flows differently depending on gravity's strength and how fast you move through space, and the differences become measurable and significant near massive objects or at high velocities. Astronauts aboard the International Space Station age slightly slower than people on Earth's surface because they travel at 70,500 miles per hour relative to the ground, and special relativity dictates that moving clocks tick slower than stationary ones from the perspective of a stationary observer. The ISS orbits 250 miles above Earth, and astronauts spend months at that altitude circling the planet every 90 minutes while travelling 5 miles every second. Time dilation from their velocity makes their clocks run slow by about 7 microseconds per day compared to Earth's surface. Simultaneously, the weaker gravity at orbital altitude makes their clocks run fast by about 14 microseconds per day, according to general relativity's predictions about gravitational time dilation. The gravitational effect overpowers the velocity effect. and astronauts aboard the ISS age about 7 microseconds faster per day than people on the ground. Over a 6-month mission lasting 180 days, an astronaut ages roughly 1.26 milliseconds more than they would have aging on Earth's surface. This effect becomes dramatic near massive objects. Black holes warp space-time so severely that time nearly stops at the event horizon from the perspective of a distant observer. Picture an astronaut falling toward a black hole while you watch from a safe distance far away. As the astronaut approaches the event horizon, you see them moving slower and slower. Light from the astronaut takes longer and longer to escape the black hole's gravitational grip and reach your eyes. The astronaut's watch appears to tick slower and slower. The astronaut's movements become sluggish, stretching into geological time, and right at the event horizon, the astronaut appears to freeze completely. Time stops. The astronaut hangs there forever from your perspective, never quite crossing the boundary, their image red-shifting into invisibility as gravity pulls their light toward infinite wavelength. The astronaut falling toward the black hole experiences something completely different. From their reference frame, nothing unusual happens to time. Their watch ticks forward at exactly 1 second per second, as it always has. They fall past the event horizon without noticing anything special at that precise moment. The point of no return comes and goes without fanfare. Only after crossing it would they realise escape became impossible, and they would have mere moments before tidal forces ripped them apart. The entire journey from event horizon to singularity might take less than 1 second for a stellar mass black hole, or minutes for a supermassive black hole millions of times more massive than the Sun. This creates the frozen star illusion. Before scientists understood black holes fully, some theorized that infalling matter would freeze at the event horizon from an external perspective, creating a dark frozen star rather than a true hole in space. The matter approaching the black hole would appear to pile up at the horizon, time-locked and static. We know now this perception arises from gravitational time dilation, and the matter does cross the horizon in its own reference frame, even though distant observers never see it happen. Supermassive black holes contain millions or billions of solar masses compressed into regions smaller than our solar system. Sagittarius A star, the supermassive black hole at the Milky Way's centre, contains 4.3 million solar masses within an event horizon roughly 17 times the Sun's diameter. Time near that event horizon runs at half the rate compared to Earth. 1 year experienced by a clock sitting just outside Sagittarius A star's event horizon corresponds to 2 years passing on Earth. Approach closer, and the effect intensifies. At 3 times the event horizon radius, time runs at 70% of Earth's rate. At twice the horizon radius, time runs at 58%. Right at the event horizon's edge, time approaches zero from an external perspective. Neutron stars provide another extreme. These stellar remnants pack more than the Sun's mass into a sphere just 12 miles wide, creating surface gravity 200 billion times stronger than Earth's. Time at a neutron star's surface runs at roughly 70% the rate, compared to deep space far from gravitational influences. 1 hour on the neutron star's surface equals 85 minutes in intergalactic space. The difference becomes significant for any process occurring near such objects. Light escaping the neutron star's gravity well loses energy, climbing out of the gravitational potential, redshifting to longer wavelengths, and arriving at distant detectors with less energy than it had when emitted. Photons essentially trade kinetic energy for gravitational potential energy during the escape. White dwarfs demonstrate measurable time dilation too. These Earth-sized stellar remnants contain roughly 1 solar mass and create surface gravity about 350,000 times stronger than what we experience. Time at a white dwarf surface runs about 99.97%, as fast as time far from any gravitational source, slowing by roughly 0.03%. Over 1 million years, a clock on a white dwarf surface would fall behind a distant clock by about 300 years. This effect becomes detectable through precise spectroscopy, because atoms at the white dwarf surface emit light at slightly redshifted wavelengths, compared to the same atoms in the laboratory on Earth. Jupiter creates time dilation too, though the effect remains tiny. Standing on Jupiter's cloud tops, time would run about 0.0002% slower than time on Earth, translating to roughly 6 milliseconds per year. the Sun's gravity at Earth's surface produces measurable time dilation compared to intergalactic space. Earth's orbital motion around the Sun contributes another tiny time dilation effect. GPS satellites must correct for both effects to maintain accuracy. The satellites orbit at altitudes where Earth's gravity is weaker, making their clocks run faster than ground clocks by about 45 microseconds per day. Simultaneously, their orbital velocity of 8,700 miles per hour makes their clocks run slower by about 7 microseconds per day. The net effect means satellite clocks gain 38 microseconds daily compared to receivers on the ground. Without correcting for this, GPS positions would drift by miles within hours, because position calculations depend on precise timing signals from multiple satellites. The speed of light creates its own time dilation, independent of gravity. Special relativity states that objects moving near light speed experience time differently than stationary observers. A spacecraft travelling at 90% of light speed would experience time running at just 44% the rate compared to Earth. 1 year aboard the spacecraft equals 2.3 years passing on Earth. At 99% of light speed, time aboard runs at 14% Earth's rate. 1 year aboard equals 7 years on Earth. At 99.9% of light speed, time crawls to just 4.5% Earth's rate, and 1 year aboard equals 22 years on Earth. This makes relativistic space travel theoretically possible from the traveller's perspective, even though the journey takes centuries or millennia from Earth's perspective. A spacecraft travelling at 99.99% of light speed could cross the galaxy's 100,000 light-year diameter in just 450 years as experienced aboard the ship, even though 100,000 years would pass on Earth. The travellers would arrive at their destination within their lifetimes, while everyone they knew on Earth had been dead for millennia. Return trips become problematic because arrival back at Earth would occur hundreds of thousands of years after departure, making the journey one way in any practical sense. Muons prove time dilation happens. These subatomic particles form when cosmic rays strike Earth's upper atmosphere. Muons decay with a half-life of 2.2 microseconds when measured at rest in a laboratory. At that decay rate, muons created 10 miles up in the atmosphere should travel just 2,000 feet before half of them decay away, and the rest should decay completely before reaching the ground. Yet we detect muons at sea level in abundance. The muons travel at 99.8% of light speed relative to Earth, and time dilation stretches their 2.2 microsecond half-life to 44 microseconds from Earth's reference frame. This gives them enough time to reach the ground before decaying. From the muon's reference frame, it experiences only 2.2 microseconds of proper time, but the distance to the ground appears contracted to just 2,000 feet due to length contraction, another relativistic effect. Both perspectives produce the same result: the muons reach the ground despite their short lifetimes. The twin paradox illustrates time dilation's weirdness. Imagine two twins. One stays on Earth, while the other travels to a star 10 light-years away at 80% of light speed, then returns at the same velocity. The journey takes 25 years from Earth's perspective, 12.5 years each way. The travelling twin experiences time dilation and ages only 15 years during the trip due to their high velocity. The travelling twin returns younger than their Earthbound sibling by 10 years. This is not an illusion or trick. The travelling twin actually ages less and their biological clock runs slower. Measurements would show fewer cell divisions, slower radioactive decay in any isotopes they carried, fewer atomic oscillations in any atomic clocks aboard their ship, everything. Gravitational time dilation near black holes enables hypothetical time travel into the future. A spacecraft could orbit close to a massive black hole, experiencing severe time dilation, while the rest of the universe ages normally outside. Spend 1 year in a tight orbit just outside a black hole's event horizon, where time runs at 10% of normal rate, and 10 years pass for the rest of the universe. Return to Earth and discover a decade has gone by. This journey remains one way because travelling backward in time appears impossible under known physics. General relativity's equations allow solutions describing closed time-like curves, where paths through space-time loop back to their starting point. But these solutions require exotic matter with negative energy density, which may not exist. Most physicists believe backward time travel violates causality and cannot occur. The distances involved in space make any human comprehension almost laughable. The light year serves as astronomy's basic unit. the distance light travels in 1 year of Earth time. Light moves at 186 days, 282 miles per second, and 1 year contains 31.5 million seconds, so 1 light year equals 5.88 trillion miles. The nearest star beyond the Sun, Proxima Centauri, sits 4.24 light years away, meaning light from that star takes 4.24 years to reach Earth, and we see it as it appeared 4.24 years ago. The star sits 24.9 trillion miles away. Journey time to Proxima Centauri with current technology staggers belief. Voyager 1, humanity's fastest spacecraft relative to the Sun, travels at 38,000 miles per hour. At that speed, reaching Proxima Centauri would require 75,000 years. The New Horizons probe, which flew past Pluto, travels at 36,000 miles per hour and would take 80,000 years. The Parker Solar Probe reaches 430,000 miles per hour during close solar passes using gravity assists, and at that maximum velocity would reach Proxima Centauri in 6,600 years. None of these missions head toward Proxima Centauri, of course, and the numbers simply illustrate how vast the distances become. Project Breakthrough. Starshot proposes using powerful lasers to push tiny spacecraft carrying microchip-sized probes up to 20% of light speed. At that velocity, the probes would reach Proxima Centauri in 20 years and send back data after another 4.24 years for light-speed communication to return. The mission remains theoretical and would require technological advances including development of powerful enough lasers, light sails capable of withstanding the acceleration, and miniaturized instruments able to survive the journey and gather useful data. Interstellar dust impacts at 20% of light speed would hit like nuclear explosions on tiny scales, and shielding the probes presents enormous challenges. The Milky Way stretches 100,000 to 180,000 light-years in diameter, depending on which population of stars you count. Travelling from one edge of the galaxy to the opposite edge at light speed would take 100,000 to 180,000 years. At Voyager 1's velocity, crossing the galaxy would require 2 billion years, longer than complex life has existed on Earth. The galaxy rotates, with the Sun completing one orbit around the galactic centre every 225 million years at a velocity of 514,000 miles per hour. The Sun has completed roughly 20 orbits since the solar system formed 4.6 billion years ago. During the last orbit, dinosaurs arose, dominated Earth, and went extinct, and mammals evolved from tiny shrew-like ancestors into every form we see today, including humans. The Andromeda Galaxy sits 2.5 million light-years away, making it the most distant object visible to the naked eye from Earth under dark skies. Light from Andromeda left that galaxy 2.5 million years ago, when human ancestors were Australopithecus, and it has been travelling through empty space toward Earth ever since, finally arriving today. We see Andromeda as it existed long before modern humans emerged as a species. The galaxy contains 1 trillion stars compared to the Milky Way's estimated 200 to 400 billion, and it spans 220,000 light-years in diameter, making it larger than our galaxy. Andromeda and the Milky Way race toward each other at 250,000 miles per hour and will collide in about 4 billion years. Although collision describes a probabilistic merging process rather than direct impacts between stars, because the space between stars is so vast that stellar collisions during galaxy mergers remain incredibly rare. The local group contains about 80 galaxies within a diameter of roughly 10 million light-years. Travelling from one edge to the opposite edge at light speed would take 10 million years. Most local group galaxies are dwarf galaxies containing a few billion stars or less. The Milky Way and Andromeda dominate the group gravitationally with Triangulum Galaxy, containing 40 billion stars, ranking as a distant third. The entire local group participates in a larger structure called the Virgo supercluster, which contains about 100 galaxy groups and clusters within 110 million light-years. The Virgo cluster sits at the supercluster's heart, containing 1,300 to 2,000 galaxies within 15 million light-years of space. The Laniakea supercluster, identified in 2014, contains the Virgo supercluster, and about 100,000 galaxies total spread across 420 million light-years. The structure's name comes from Hawaiian and means immeasurable heaven. Laniakea contains the mass of 100 million billion suns distributed through this volume, and galaxies within it follow gravitational flows toward a central region called the Great Attractor. The entire supercluster moves coherently through space, bound together by gravitational interactions that override cosmic expansion on these scales. Crossing Laniakea at light speed would require 520 million years, and at Voyager speeds would take 10 trillion years, about 750 times the current age of the universe. The observable universe extends 46 billion light-years in every direction from Earth, creating a sphere 93 billion light-years in diameter. This volume contains an estimated 2 trillion galaxies, though that number remains uncertain and recent studies suggest it might be lower. The observable universe boundary marks the limit of what light has had time to reach since the Big Bang 13.8 billion years ago, accounting for expansion during the photon's journey. Beyond this boundary, light from more distant regions has not reached Earth yet, and due to acceleration, never will. The universe beyond what we can observe might extend infinitely in all directions, or might curve back on itself in ways we cannot yet determine. Crossing the observable universe at light speed would take 93 billion years, about 7 times longer than the universe has existed. At Voyager speeds, the journey would require 1.8 million trillion years. These numbers lose meaning because they exceed any practical reference point. The scale breaks human brains trying to comprehend it. Light from the most distant galaxies we observe has travelled 13.4 billion years to reach our telescopes, meaning we see those galaxies as they appeared just 400 million years after the Big Bang, when the universe was 3% of its current age. The galaxies appear as small, irregular collections of stars undergoing their first burst of star formation. Those same galaxies sit 30 billion light-years away now, due to expansion during the photon's journey, and we will never see what they look like today because light showing their current state left those galaxies 13.4 billion years ago and has not reached us yet, and by the time it would reach us, more time will have passed showing an even later state. Temperature extremes in space range from effectively absolute zero to billions of degrees in stellar cores. The coldest natural place in the universe is the Boomerang Nebula, a cloud of gas expelled by a dying star located 5,000 light-years from Earth. Gas in the nebula's coldest regions measures 1 Kelvin, just 1 degree above absolute zero where all thermal motion ceases. The nebula formed when a dying star ejected its outer layers into space, and the rapid expansion of that gas cooled it dramatically through a process similar to how aerosol cans get cold when you spray them. The expansion does work against the surrounding pressure, converting thermal energy into kinetic energy and dropping the temperature. Absolute zero sits at negative 459.67 degrees Fahrenheit, or negative 273.15 degrees Celsius, and reaching this temperature remains impossible according to the third law of thermodynamics. Cooling matter toward absolute zero becomes exponentially more difficult as you approach it, because extracting the final bits of thermal energy requires more and more energy input. Atoms at 1 Kelvin barely vibrate. Electrons orbit atomic nuclei in their lowest energy states. Chemical reactions stop because molecules lack the energy to overcome reaction barriers. Gases condense into liquids or solids. Quantum mechanical effects dominate, and particles behave in ways classical physics cannot explain. The coldest temperature ever achieved in a laboratory reached 38 trillionths of a degree above absolute zero, when researchers at MIT cooled sodium atoms using laser cooling and magnetic trapping techniques. At such temperatures, atoms slow to nearly stationary, and quantum effects cause them to merge into a single quantum state called a Bose-Einstein condensate, where individual atoms lose their separate identities and behave as one coherent quantum object. The condensate demonstrates weird quantum behavior normally hidden at room temperature, including superfluidity, where the condensate flows without friction and can climb up container walls against gravity. Cosmic background radiation fills all of space with microwave photons at 2.7 Kelvin, establishing a minimum temperature for any object in the universe that cannot shield itself from this radiation. You cannot cool below 2.7 Kelvin passively because you constantly absorb energy from the background photons. Active cooling can overcome this, but requires expending energy. The cosmic background temperature drops as the universe expands, and in the distant future will approach absolute zero as expansion continues forever. Stellar cores reach temperatures of 15 million Kelvin in stars like the Sun. At these temperatures, Hydrogen nuclei move fast enough to overcome electromagnetic repulsion and fuse together through quantum tunneling, releasing energy that powers the star. More massive stars achieve higher core temperatures. A star 8 times the Sun's mass burns at 30 million Kelvin. A star 20 times solar mass reaches 50 million Kelvin. These extreme temperatures arise because the star's mass creates gravitational pressure that squeezes the core, converting gravitational potential energy into thermal energy through the virial theorem. Larger mass means stronger gravity, which means more compression, which means higher temperature. Supernovae explosions reach temperatures of 100 billion Kelvin in their cores during the collapse and rebound. When a massive star exhausts its nuclear fuel, the core collapses in less than 1 second, crushing matter to nuclear densities and rebounding in a shockwave that blows the star apart. The enormous energy released during core collapse heats material to temperatures where photons carry enough energy to create matter-antimatter pairs spontaneously from vacuum fluctuations. And neutrinos reach such high densities they interact with matter, despite being nearly massless and typically passing through planets without noticing. The shock wave propagates outward through the star's layers, heating them to billions of degrees and synthesizing heavy elements through rapid neutron capture, before flinging this material into space to seed future generations of stars and planets. Neutron star cores may reach 1 trillion Kelvin at their centers. These stellar remnants pack more than the Sun's mass into a sphere 12 miles wide, creating pressures that squeeze protons and electrons together into neutrons and compress those neutrons to densities where they touch each other. A teaspoon of neutron star material weighs 1 billion tons. The exact state of matter at these densities remains uncertain because we cannot recreate such conditions in laboratories. Theoretical physics predicts matter might break down into free quarks, forming a quark-gluon plasma, or might form exotic states like strange quark matter that might be more stable than normal matter. Some theories predict neutron star cores could contain tiny black holes that slowly consume the star from the inside. Quasars generate temperatures exceeding 10 trillion Kelvin in the accretion disks surrounding their supermassive black holes. These objects, powered by black holes containing millions to billions of solar masses, shine brighter than entire galaxies. Matter falling toward the black hole forms a spinning disk that heats through friction and gravitational compression to temperatures where atoms ionize completely and the plasma emits X-rays and gamma rays. Quasars put out so much energy they can be seen across billions of light years, making them the brightest steady light sources in the universe. The most luminous quasars generate energy equivalent to 100 trillion suns, packed into a region the size of our solar system. Gamma-ray bursts briefly produce even higher temperatures approaching 100 trillion Kelvin in jets of material ejected at 99.999% of light speed. These jets form when massive stars collapse into black holes, or when neutron stars merge together. The collapsing material's rotation funnels some fraction along the rotation axis, accelerating it to relativistic speeds through mechanisms still not fully understood. The jets slam into surrounding material, creating shock waves that heat gas to enormous temperatures. For a few seconds, a gamma-ray burst can outshine all other gamma-ray sources in the observable universe combined. If a gamma-ray burst occurred within 6,000 light-years of Earth, with its jet pointed at us, the radiation would devastate the atmosphere, destroying the ozone layer and exposing Earth's surface to lethal solar and cosmic radiation. Some scientists speculate that gamma-ray bursts might have caused past mass extinctions by sterilizing portions of the planet facing the burst. The Large Hadron Collider creates the hottest temperatures achieved by humans, reaching 5 trillion Kelvin when heavy ions collide at near-light speed. These collisions recreate conditions that existed microseconds after the Big Bang, when the universe was hot and dense enough that quarks and gluons moved freely rather than being confined inside protons and neutrons. The plasma created in these collisions lasts just 10 to the negative 23 seconds before expanding and cooling, but during that brief existence, physicists measure its properties to understand how matter behaved in the early universe. The collisions confirmed that the quark-gluon plasma behaves more like a perfect fluid with nearly zero viscosity rather than like a gas, and this discovery reshaped understanding of the early universe's evolution. Strange objects populate space in configurations that defy terrestrial experience. Neutron stars spin up to 716 times per second. with their surfaces moving at 20% of light speed. These stellar remnants form when massive stars explode as supernovae, and conservation of angular momentum during core collapse causes the rotation to accelerate dramatically. The original star might have rotated once every 30 days like the Sun, but when the core collapses from thousands of miles in diameter to just 12 miles wide, rotation speeds up by a factor of millions. The fastest known pulsar, PSR J2748-2446 AD, completes 716 rotations every second, and its equatorial surface races through space at 43,000 miles per second. Approaching the light speed limit, material at the equator experiences enormous centrifugal forces trying to fling it into space, and the neutron star holds itself together only through gravity so intense that space-time curves measurably around it. Pulsar timing precision exceeds the best atomic clocks humans build. Some pulsars maintain rotation periods stable to within 1 part in 10 to the 15, meaning the pulsar gains or loses less than 1 microsecond every 32,000 years. This stability arises because neutron stars have essentially no internal friction to slow rotation. Normal stars contain turbulent gas that creates drag, but neutron star interiors consist of matter so dense it behaves as a superfluid, flowing without friction. The crust consists of crystallized neutron-rich nuclei arranged in a perfect lattice, eliminating energy dissipation that would occur in ordinary matter. Pulsars slow down gradually as they radiate electromagnetic energy into space, but the slowdown occurs at predictable rates that allow astronomers to measure pulsar properties with extreme precision. Magnetars generate the strongest magnetic fields in the universe, reaching 100 trillion times Earth's magnetic field strength. These neutron stars concentrate magnetic energy density so intense that the vacuum near their surface becomes birefringent, splitting light into separate polarization modes like calcite crystals do, but trillions of times more strongly. The magnetic field's energy exceeds the star's gravitational binding energy, making magnetars unstable and prone to sudden reconfigurations called starquakes. When the crust fractures, it releases magnetic energy equivalent to thousands of supernovae compressed into milliseconds. The December 2004 starquake from magnetar SGR 1806-20, located 50,000 light-years away, released more energy in 1/10 of a second than the Sun emits in 150,000 years. And the burst affected Earth's ionosphere despite the enormous distance. Human technology near a magnetar would fail instantly. The field would disrupt molecular bonds because the magnetic force on electron orbitals would exceed electromagnetic forces holding atoms together. Matter would stretch into needle shapes pointing along field lines. The field would extract kinetic energy from any moving charged particle, stopping it within microseconds. A human body placed near a magnetar would experience forces tearing individual atoms apart. Iron atoms in blood would align with the field and experience forces trying to rearrange molecular structure. Neurons would malfunction as ion channels disrupted. Death would occur instantly from multiple failures across all biological systems. Rogue planets drift through interstellar space untethered to any star. Recent estimates suggest the Milky Way contains billions of these orphan worlds, potentially outnumbering stars. Some rogue planets formed around stars and were ejected through gravitational interactions with other planets or passing stars. Others formed directly from collapsing gas clouds, following the same process that creates stars, but without gathering enough mass to ignite fusion. These worlds travel through space in darkness, their surfaces frozen at temperatures near absolute zero, unless internal heat from radioactive decay or residual formation energy provides warmth. A planet ejected after formation might retain a thick hydrogen atmosphere that provides greenhouse warming, keeping subsurface oceans liquid despite the absence of stellar radiation. Some rogue planets might harbour life. Jupiter's moon. Europa contains a subsurface ocean heated by tidal flexing, as Jupiter's gravity needs the moon's interior. A rogue planet with a large moon could maintain similar tidal heating indefinitely while travelling between the stars. Heat from the planet's core combined with tidal heating could keep water liquid for billions of years, providing an environment where life might emerge and evolve in total darkness, feeding on chemical energy from hydrothermal vents on the ocean floor rather than sunlight. Detecting such life would be nearly impossible, because rogue planets emit almost no light, and and finding them requires luck or comprehensive infrared surveys searching for their faint thermal emission. Quasars illuminate the early universe. These objects formed when supermassive black holes in the centers of young galaxies consumed gas at prodigious rates during the universe's first billion years. The most distant quasar discovered so far, J313 1806, shines from 13.03 billion light-years away, meaning its light left when the universe was just 670 million years old. The quasar contains a black hole of 1.6 billion solar masses, and explaining how black holes grew so large so quickly challenges current theories of black hole formation and growth. Black holes grow by accreting matter and merging with other black holes, and simulations struggle to produce billion solar mass black holes in less than 700 million years, starting from stellar mass seeds formed by the first generation of stars. Some scientists propose that supermassive black holes form directly from collapsing gas clouds in the early universe, without going through a stellar phase. These direct collapse black holes could start with masses of 10,000 to 100,000 solar masses, giving them a head start on growth. Others propose that dense star clusters in early galaxies underwent runaway collisions, creating very massive stars that collapsed directly into intermediate mass black holes, which then grew through mergers and accretion. Distinguishing between these scenarios requires observing black holes from even earlier times, and upcoming telescopes may find quasars from when the universe was just 500 million years old, further constraining how quickly supermassive black holes formed. Hypervelocity stars race through the galaxy at speeds exceeding 1,000 miles per second, fast enough to escape the Milky Way's gravity entirely. These stars gain their extreme velocities through close encounters with the supermassive black hole at the galaxy's center. When a binary star system wanders too close, tidal forces from the black hole can capture one star while flinging the other away at enormous speed. The ejected star shoots out of the galactic core like a slingshot, crossing the galaxy in 100 million years. Dozens of hypervelocity stars have been identified, some traveling fast enough that they will leave the Milky Way entirely and spend eternity crossing the void between galaxies. One star, US 708, travels at 2.6 million miles per hour, twice the escape velocity from our galactic neighborhood. Diamond worlds exist in space. White dwarfs composed primarily of carbon cool over billions of years, and as interior temperatures drop, carbon crystallizes into diamond. The entire star becomes a diamond crystal the size of Earth, with a thin atmosphere of hydrogen or helium above. One such object, BPM 37093, located 50 light-years away, contains an estimated 10 billion trillion carats of diamond, a mass roughly equal to our moon. The diamond interior remains hidden beneath layers of carbon and oxygen that have not yet crystallized. Over trillions of years, as the white dwarf continues cooling, more layers will crystallize from the center outward until the entire star becomes solid diamond, a glittering stellar corpse radiating faint heat into the void. Some exoplanets might be diamond worlds too. Planets forming in carbon-rich systems where the carbon-to-oxygen ratio exceeds, one could develop mantles and crusts made of diamond and silicon carbide, rather than the silicate minerals common on Earth. These worlds would glitter under their parent star's light if they had no atmospheres, although most would likely retain thick atmospheres that obscure their surfaces. 55 Cancri E, an exoplanet 8 times Earth's mass orbiting a sun-like star 40 light-years away, may be a carbon planet with a diamond interior. Observations of the planet's mass and radius combined with its host star's carbon-rich composition suggest diamond could comprise up to 1/3 of the planet's mass. Surface temperatures exceeding 4,000 degrees Fahrenheit would keep any diamond molten, creating seas of liquid carbon rather than solid crystals. Violence in space dwarfs anything Earth experiences. Galaxies collide and merge, triggering waves of star formation as gas clouds slam together and compress. The Milky Way and Andromeda galaxies will merge in approximately 4 billion years, and the collision will reshape both galaxies completely. As the galaxies approach, gravity will distort both structures, pulling out long tidal tails of stars stretching millions of light-years into space. The first pass through each other will be just the beginning because gravity pulls the galaxies back together. Multiple passes over hundreds of millions of years will occur before the galaxies finally settle into a single giant elliptical galaxy. During these passes, close encounters between stars remain rare because space between stars is vast, but gas clouds collide and compress, igniting massive star formation episodes. Earth's sky will transform during this merger. Andromeda will appear larger than the full moon long before the merger begins, because the galaxy subtends several degrees across as it approaches. The galaxy's core will brighten as compression heats gas, making Andromeda visible in daylight during the merger's peak. Star formation bursts will light the sky with brilliant blue star clusters and reddish nebulae where new stars condense. Close passes might fling the solar system into a different orbit around the newly merged galaxy's centre, though direct stellar collisions with our Sun remain extraordinarily unlikely. The Sun itself will be approaching its red giant phase by then, expanding to engulf Mercury and Venus and possibly Earth, making any galaxy collisions secondary to humanity's more immediate stellar crisis. Supernovae explosions release more energy in seconds than the Sun will emit in its entire 10 billion year lifetime. When a star 8 times more massive than the Sun exhausts its nuclear fuel, the core collapses catastrophically in under 1 second, crushing matter to nuclear densities and rebounding in a shockwave that destroys the star. The explosion accelerates material to 10% of light speed and heats it to billions of degrees. Brightness peaks at 10 billion times the Sun's luminosity, making the supernova briefly visible from billions of light years away. The expanding debris slams into surrounding space at 30,000 miles per second, sweeping up interstellar gas and creating a bubble of hot plasma hundreds of light years wide. Supernova remnants reshape the galaxy. The Crab Nebula, remnant of a supernova witnessed by Chinese astronomers in 1054 CE, spans 11 light years across and continues expanding at 3.4 million miles per hour. A pulsar at its heart spins 30 times per second, powering the nebula's glow with radiation and particles. The nebula emits radiation across the electromagnetic spectrum from radio waves through gamma rays, and studying this emission reveals how supernova explosions create elements and accelerate cosmic rays. The shockwave will eventually fade as it merges with the general interstellar medium, but for now it serves as a laboratory for extreme physics, where particles reach energies that dwarf anything achievable in human-built accelerators. Gamma-ray bursts rank as the most powerful explosion since the Big Bang. These events release as much energy in 10 seconds as the Sun will emit in its entire lifetime. Long-duration bursts lasting more than 2 seconds come from massive stars collapsing into black holes. Short-duration bursts lasting under 2 seconds come from neutron star mergers. Both scenarios produce jets of material moving at 99.99% of light speed, and these jets concentrate the explosion's energy into narrow beams. If Earth lies in the beam's path, we detect the burst. If the beam points elsewhere, we see nothing despite the explosion's power. GRB 080-916C remains the most powerful burst ever detected, releasing energy equivalent to 10,000 suns converting their entire mass into pure energy via Einstein's equation E=mc². The burst occurred 12.2 billion light-years away when the universe was just 1.5 billion years old. Despite the enormous distance, the gamma rays reached Earth with enough intensity to trigger detectors on multiple satellites. If such a burst occurred in our galaxy, it would devastate life on planets within thousands of light-years. Radiation would strip Earth's atmosphere, destroy the ozone layer, create nitrogen oxides that would block sunlight and poison ecosystems, and expose the surface to lethal doses of cosmic rays. Some scientists propose that a nearby gamma-ray burst might have caused the Ordovician extinction 450 million years ago that killed 85% of marine species, though direct evidence remains elusive. Asteroid impacts deliver planet-altering violence. The Chicxulub impact 66 million years ago released energy equivalent to 10 billion Hiroshima bombs when a 6-mile-wide asteroid struck the Yucatan Peninsula at 45,000 miles per hour. The impact excavated a crater 110 miles wide and 12 miles deep in seconds. Shockwaves rippled through the planet, triggering earthquakes, magnitude 11 on the Richter scale. Tsunamis 300 feet tall radiated outward. Debris launched into space fell back through the atmosphere as white-hot meteors, heating the air to oven-like temperatures and igniting wildfires across continents. Dust and soot darkened the sky for months, collapsing photosynthesis and causing global temperatures to drop by 50 degrees Fahrenheit. 3/4 of all species went extinct, including every non-avian dinosaur. Larger impacts have occurred. The asteroid that formed South Africa's Red Fort crater 2.02 billion years ago measured 12 miles wide and created a crater 180 miles across. The impactor travelled 45,000 miles per hour and released energy equivalent to 1 billion megatons, roughly 60 times the Chicxulub impact. The crater eroded over 2 billion years, but geological studies reveal the impact scale. Rock layers melted and flowed like liquid. Shatter cones formed where shock waves compressed rock beyond breaking point. The impact ejected debris across southern Africa and may have triggered the first widespread extinction in Earth's history, eliminating many early single-celled organisms. The Moon's formation resulted from a Mars-sized object striking Earth 4.5 billion years ago. This collision, called the Big Splash or Giant Impact Hypothesis, remains the leading explanation for why Earth has such a large moon relative to its size, and why moon rocks share similar composition to Earth's mantle. The impact vaporized the impactor and part of Earth's crust, creating a disk of debris that orbited Earth and coalesced into the Moon over millions of years. The collision tilted Earth's rotation axis to 23.5 degrees, creating our seasons. It also added angular momentum that made Earth spin faster, with day lengths of just 5 hours immediately after the impact. Tidal interactions with the Moon have gradually slowed Earth's rotation over billions of years to today's 24-hour day. Emptiness defines space more than anything else. The average density of matter in the universe equals about 6 hydrogen atoms per cubic meter, roughly 10 to the negative 27 kilograms per cubic meter. Compare this to Earth's atmosphere at sea level containing 10 to the 25 molecules per cubic meter, or water containing 10 to the 28 molecules per cubic meter. The universe averages 1 trillionth the density of water. Most of this matter concentrates in stars, planets, and galaxies, leaving the space between stars and galaxies nearly empty. Intergalactic space averages 1 atom per cubic meter, and some voids contain just 1 atom per 10 cubic meters. The space between planets seems empty by human standards, but contains roughly 10 million atoms per cubic meter near Earth's orbit, mostly hydrogen from the solar winds streaming off the Sun. This density drops rapidly with distance from the Sun. At Pluto's orbit, the density falls to 1,000 atoms per cubic meter. Beyond the heliopause at 120 astronomical units where the Sun's influence ends, interstellar space begins with just 0.1 atoms per cubic meter in the local bubble, the low-density cavity in the interstellar medium where our solar system resides. Interstellar clouds represent the densest regions of space outside stellar systems, containing 100 to 1 million atoms per cubic meter, depending on the cloud's type and evolution. Giant molecular clouds where stars form can reach densities of 10 million atoms per cubic meter in their cores, still 1 trillion times less dense than Earth's atmosphere. These clouds collapse under their own gravity over millions of years, fragmenting into clumps that become individual stars. The gravitational collapse concentrates matter dramatically, with stellar core densities reaching 100 grams per cubic centimeter, about 7 times denser than lead. Galaxies occupy just circles 1% of cosmic volume, but contain virtually all visible matter. The Milky Way's stellar disk spans 100,000 light-years, but contains roughly 200 billion stars averaging 1 solar mass each, distributed through a volume of 10 million cubic light-years. This works out to an average of 1 star per 50,000 cubic light-years, or 1 sun-like mass per 4,000 trillion cubic miles. Space between stars sits nearly empty with density dropping to 0.1 atoms per cubic meter, except in nebulae and molecular clouds. The space between galaxies holds even less. Intergalactic medium density averages 1 atom per cubic meter in the cosmic web's filaments where galaxies cluster, dropping to 0.01 atoms per cubic meter in voids between filaments. These voids occupy roughly 80% of cosmic volume, but contain less than 5% of matter. The largest voids span hundreds of millions of light-years and contain so little matter that a traveller could cross them for 100 million light-years without encountering a single galaxy brighter than the Milky Way. This emptiness means that interstellar travel would involve passing through near vacuum for years or centuries. A spacecraft traveling to Proxima Centauri would encounter roughly 40 billion atoms total during the 4.24 light-year journey, most of them hydrogen. At high speeds, even these sparse atoms become dangerous. Impacting hydrogen atoms at 10% of light speed would release energy equivalent to high-energy protons in particle accelerators. Accumulated impacts would heat the spacecraft's surface and erode it over time. Dust grains, though rare, would impact like bullets. A grain 1/10 of a millimeter across hitting at 10% light speed would release energy equivalent to 100 tons of TNT, punching through any conventional shielding. Radiation permeates the emptiness. Cosmic rays, high-energy particles accelerated by supernova shockwaves and other violent processes, constantly bombard every location in space. Earth's atmosphere and magnetic field protect the surface from these particles, but space travelers would face continuous exposure. Galactic cosmic rays contain mostly protons traveling at 80 to 99% of light speed with energies ranging from millions to billions of electron volts. These particles pass through spacecraft walls, depositing energy in any material they encounter, including human tissue. Long-duration space missions beyond Earth's magnetosphere would expose astronauts to radiation doses 100 to 1,000 times higher than on Earth's surface. A trip to Mars lasting 2 years would expose crew to 0.6 sieverts of radiation, roughly equivalent to having full-body CT scans every week for 2 years. This increases lifetime cancer risk by about 3%. Deep space missions lasting decades would accumulate lethal doses without heavy shielding. Shielding against cosmic rays presents challenges because stopping high-energy particles requires significant mass, and adding mass makes spacecraft more expensive to launch and harder to accelerate. Some particles possess such high energy that stopping them requires shielding several meters thick. Solar radiation adds danger during solar storms. The Sun occasionally releases coronal mass ejections that accelerate protons and electrons to high energies. These solar particle events can deliver radiation doses exceeding safe limits in hours during the worst storms. The August 1972 solar particle event would have killed astronauts on the lunar surface within hours had the Apollo 16 and 17 missions occurred during the storm instead of months before and after it. Shielding against solar particle events requires less mass than cosmic ray shielding because solar particles carry lower energies, but spacecraft need dedicated storm shelters where crew can retreat during events. Galactic cosmic rays also damage electronics. High-energy particles passing through computer chips can flip bits in memory, causing errors in calculations and corrupting data. Space-qualified electronics use radiation-hardened designs with redundant systems and error-checking codes, but these components lag behind consumer technology by 10 to 20 years because radiation hardening requires extensive testing and validation. The electronics aboard the Hubble Space Telescope use processors from the 1980s because those chips have been proven to withstand radiation. More modern electronics would fail within months or years. Cosmic rays create secondary particles when they collide with spacecraft walls or lunar regolith. Neutrons, pions, and other particles spray out from impact sites, creating a shower of radiation that bounces around the spacecraft interior. Thick shielding actually makes this worse because more collisions produce more secondary particles. Hydrogen-rich materials like water, polyethylene, or liquid methane provide better shielding than metal because hydrogen nuclei absorb high-energy protons more effectively and produce fewer dangerous secondaries. Some spacecraft designs propose surrounding crew compartments with water tanks that serve dual purposes as both radiation shields and life support reserves. Black holes warp space so severely that they trap light itself. The event horizon marks the boundary beyond which escape becomes impossible. Once anything crosses this threshold, not even light moving at maximum speed through space-time can climb back out of the gravitational well. The horizon appears as a spherical surface surrounding the singularity where matter crushes to infinite density and space-time curvature becomes infinite. The size of the event horizon depends only on the black hole's mass. A black hole containing one solar mass would have a horizon 3.7 miles in diameter. A black hole containing 10 solar masses would have a horizon 37 miles wide. Sagittarius A star at the galaxy's center contains 4.3 million solar masses and has a horizon 15.5 million miles in diameter, roughly 18 times the Sun's diameter. Tidal forces near stellar mass black holes would shred any object long before it reached the event horizon. The gravitational field strength increases so rapidly with decreasing distance that the difference in gravity between an object's near side and far side exceeds the material strength holding the object together. For a 1 solar mass black hole, these tidal forces become lethal at about 250 miles from the horizon, a distance roughly equal to 20 horizon radii. A human falling feet first towards such a black hole would experience perhaps 10 million times Earth's gravity pulling on their feet and slightly less pulling on their head. The difference would stretch the body into a thin stream of atoms in a process astronomers call spaghettification. Supermassive black holes create gentler tides at their horizons due to their enormous size. The tidal force scales inversely with the square of the black hole's mass, so a billion solar mass black hole creates tidal forces 1 trillion times weaker than a 1 solar mass black hole at their respective horizons. An astronaut could cross the event horizon of the supermassive black hole at the center of a distant galaxy without experiencing fatal tidal forces immediately. Only after falling deeper inside would the increasing gravity gradient tear them apart. The astronaut would have several minutes to observe their surroundings before spaghettification occurred. They would see strange optical effects caused by the extreme space-time curvature, with light from the outside universe concentrated into a bright ring behind them, while everything ahead appeared dark as light from that direction got swallowed by the singularity. Black holes rotate, dragging space-time along with them in a phenomenon called frame dragging. The rotating black hole creates an ergosphere region outside the event horizon, where space-time itself rotates, and any object in this region must rotate with it regardless of any effort to remain stationary. The ergosphere boundary touches the event horizon at the poles and bulges out to twice the horizon radius at the equator. Within the ergosphere, space-time rotates at speeds approaching light speed near the horizon. An object dropped from outside would begin rotating as soon as it entered the ergosphere, pulled along by the rotating space-time like leaves caught in a whirlpool. The Penrose process extracts energy from rotating black holes by dropping matter into the ergosphere on trajectories that split into 2 pieces, with one piece falling into the black hole while the other escapes with more energy than the original object possessed. The extra energy comes from the black hole's rotation, which slows slightly to conserve angular momentum. This process could theoretically power advanced civilizations by dumping garbage into rotating black holes and harvesting the energy output. The maximum efficiency approaches 29% for maximally rotating black holes, far exceeding the 0.7% efficiency of nuclear fusion. A civilization capable of building structures around black holes could extract more energy from spinning stellar mass black holes than from burning all matter in several stars. Quantum mechanics near black holes predicts they emit Hawking radiation, thermal radiation created when quantum vacuum fluctuations near the horizon produce virtual particle-antiparticle pairs where one particle escapes to infinity while the other falls into the black hole. The escaping particles carry positive energy, while the infalling particles carry negative energy relative to distant observers, slowly reducing the black hole's mass. The radiation temperature depends inversely on mass, with stellar mass black holes emitting radiation at temperatures far below the cosmic microwave background, and thus absorbing more energy than they radiate. Small black holes emit hotter radiation. A black hole containing the mass of Mount Everest would glow at room temperature. A black hole containing an asteroid's mass would emit X-rays. Microscopic black holes would explode in gamma-ray bursts within seconds of forming. Hawking radiation causes black holes to evaporate given enough time. A 1 solar mass black hole would take 10 to the 67 years to evaporate completely, far longer than the current age of the universe by a factor of 10 to the 57. Supermassive black holes take even longer, with billion solar mass black holes requiring 10 to the 100 years. These timescales exceed any practical meaning, but in the far future, when stars have exhausted their fuel and galaxies have dispersed into darkness, black holes will represent the last surviving structures, slowly evaporating through Hawking radiation until even they disappear, and nothing remains but cold diffuse particles spreading through ever-expanding space. Dark matter comprises 85% of all matter in the universe, despite remaining completely invisible. This mysterious substance interacts only through gravity, never absorbing, emitting, or scattering light. We detect dark matter through its gravitational influence on visible matter, on light passing through space, and on the large-scale structure of the universe, galaxies rotate faster than visible matter can account for. The Milky Way rotates at 514,000 miles per hour at the Sun's location, 26,000 light-years from the galactic center. At this distance, and with only visible matter providing gravity, the expected velocity should be 280,000 miles per hour. The excess velocity requires additional unseen mass distributed through a halo surrounding the galaxy. Measurements show dark matter. Halos extend well beyond visible disks, with mass totals reaching 10 times the visible stars and gas. Galaxy clusters reveal dark matter through gravitational lensing. Light from background galaxies bends as it passes through the cluster's gravitational field, and measuring this bending allows mapping the cluster's total mass distribution. The lensing reveals far more mass than visible matter can account for. The Coma cluster contains roughly 100 times more dark matter than visible matter. The Bullet cluster, created by two galaxy clusters colliding, shows separated distributions of visible matter and dark matter. X-ray images show hot gas from both clusters interacting and stopping at the collision site. Gravitational lensing shows the bulk of mass continue through the collision, proving dark matter behaves differently than ordinary matter because it does not collide with itself or with ordinary matter beyond gravitational interaction. Dark matter's composition remains unknown. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical particles predicted by supersymmetry theories that would interact through gravity and the weak nuclear force. Experiments around the world search for WIMPs by detecting rare collisions between dark matter particles and atomic nuclei in ultra-sensitive detectors shielded from cosmic rays deep underground. Decades of searching have found no confirmed detections, constraining properties these particles could have and ruling out many theoretical models. Alternative candidates include axions, ultra-lightweight particles predicted by quantum chromodynamics theories. Sterile neutrinos, massive cousins of ordinary neutrinos, represent another possibility. Primordial black holes formed in the early universe could comprise some fraction of dark matter. These black holes would have formed from density fluctuations shortly after the Big Bang, long before stars existed. Black holes with masses between 10 to the -8 and 10 solar masses could exist without conflicting with observational constraints. Recent detections of surprisingly massive black holes merging in gravitational wave signals hint that primordial black holes might be common, though conventional formation channels from stellar collapse can also explain these events. Dark energy remains even more mysterious, comprising 68% of the universe's total energy, while producing a repulsive pressure that accelerates cosmic expansion. This energy appears uniformly distributed through space with a constant density that does not dilute as the universe expands, meaning new dark energy continuously appears in newly created space. The simplest explanation treats dark energy as a cosmological constant, an intrinsic energy density of empty space itself arising from quantum vacuum fluctuations. Quantum field theory predicts vacuum energy should exist, but calculations produce values 10 to the 120 times larger than observations allow, representing perhaps the worst prediction in physics history. Alternative theories propose that dark energy varies in strength over time or across space, with its current value determined by scalar field dynamics similar to the Higgs field. These quintessence models require less fine-tuning than a cosmological constant, but lack compelling evidence. Modified gravity theories attempt to explain acceleration without dark energy by changing how gravity works on cosmological scales, but these theories struggle to match observations across multiple contexts. Most cosmologists favor the cosmological constant explanation, despite its theoretical problems, because it matches observations with just one parameter. Dark energy will determine the universe's ultimate fate. If dark energy remains constant, the universe will expand forever with acceleration continuing indefinitely. Galaxies beyond the local group will recede beyond our cosmic horizon within 100 billion years, as space between us and them expands faster than light can cross. Star formation will cease when galaxies exhaust their gas supplies roughly 1 trillion years from now. Stars will burn out over tens of trillions of years, leaving behind white dwarfs, neutron stars, and black holes. Even these remnants will eventually decay, with white dwarfs crystallizing into black dwarf spheres and black holes evaporating through Hawking radiation over 10 to the 100 years, the universe will fade into a cold, dark, empty state with nothing but isolated particles separated by light years, expanding forever into the void. Alternative scenarios exist if dark energy evolves over time. If dark energy strengthens with age, the universe could end in a big rip, where acceleration becomes so intense it tears apart galaxies, stars, planets, and eventually atoms themselves. Calculations suggest this could occur as soon as 22 billion years from now if dark energy's strength increases at certain rates. The Milky Way would unbind 60 million years before the rip. The solar system would unbind 3 months before. Earth would explode 30 minutes before. Atoms would shred in the final moments as electromagnetic forces could no longer overcome expansion, pulling nuclei and electrons apart. If dark energy weakens or reverses sign, expansion could slow and eventually reverse, causing the universe to collapse in a big crunch. All matter would fall together, with galaxies colliding and merging as space contracted. Temperature would rise as compression heated everything. The cosmic microwave background would blue shift into visible light, then X-rays, then gamma rays as wavelengths compressed. The universe would return to a hot, dense state similar to the Big Bang, potentially bouncing into a new expansion phase in cyclic cosmology models. Current observations favour eternal expansion with constant dark energy, but uncertainty remains. Measurements of dark energy's properties have error bars allowing small variations that could make dramatic differences over billions of years. Future observations will constrain these properties better, determining whether the universe faces cold dark expansion, violent ripping, or hot collapse. For now, the most likely future involves a universe that expands forever, growing emptier and darker until nothing remains but quantum fluctuations in an endless void. These facts about space reshape perspective on humanity's place in existence. We live on a world orbiting an average star in an ordinary galaxy in an unremarkable region of an unimaginably vast universe governed by physical laws that permit conditions hospitable to life in just tiny fractions of space and time. The cosmos contains wonders that dwarf human accomplishment and timescales that make human history a blink. Matter and energy exist in forms and states impossible to recreate on Earth. Forces operate at extremes that would vaporize our world instantly if we encountered them directly. Distances separate us from neighbors by voids we cannot cross with current technology. The universe appears hostile to life across most of its volume and across most of its history, with brief windows of habitability arising when stars form in the right proportions, with the right chemistry at the right times. Yet here we are, conscious beings capable of studying the cosmos and understanding our situation. We have measured cosmic distances, probed extreme conditions, detected invisible matter, and traced the universe's evolution from the Big Bang to the present. We live in a golden age for astronomy when telescopes can observe the farthest reaches of space and time. Future generations might lose this opportunity as dark energy pushes distant galaxies beyond visibility. We occupy a special moment in cosmic history when the universe has existed long enough for intelligence to emerge, but has not existed so long that evidence of the Big Bang and cosmic structure has faded beyond detection. If we inhabit the void, at least we possess tools to understand that truth and imagine what lies beyond. The search for life beyond Earth operates within these constraints. Humanity has spent decades listening for radio signals from extraterrestrial civilizations, scanning billions of frequency channels across thousands of star systems. The search for extraterrestrial intelligence, SETI, assumes any sufficiently advanced civilization would develop radio technology and might broadcast signals either intentionally or as leakage from their communications infrastructure. Radio waves travel at light speed and penetrate interstellar gas and dust that would block optical wavelengths, making them ideal for interstellar communication. Earth's radio bubble, the expanding sphere of radio emission from human broadcasts, currently extends roughly 100 light-years in all directions, containing about 14,000 stars within its volume. Any civilization within that bubble could detect Earth's presence if they pointed sufficiently sensitive receivers in our direction and happened to be listening at frequencies we broadcast. The Arecibo message transmitted in 1974 aimed at globular cluster M13, located 25,000 light-years away, will reach its target in the year 26,974. Any response would arrive in 15974, assuming instant reply. This illustrates the fundamental challenge of interstellar communication across vast distances when limited by light speed. Conversations become impractical. Messages take decades or centuries for one-way transmission, and any exchange of information requires timescales exceeding human lifetimes. Detection of technosignatures offers hope for finding evidence of intelligence without direct communication. Technosignatures include any observable phenomena that would indicate technological civilization, such as atmospheric pollution from industrial chemistry, heat signatures from energy consumption, artificial illumination visible in nighttime spectra, or engineering projects that modify star systems. The most famous proposed technosignature remains the Dyson sphere, a hypothetical megastructure that would surround a star to capture its total energy output. Such a structure would make the star invisible in optical wavelengths, while creating a powerful infrared signature as waste heat radiated into space. Astronomers search for stars with unusual infrared excess that might indicate partial Dyson structures under construction, or Dyson swarms of smaller collectors. Tabby's star, officially designated KIC 8462852, briefly excited speculation about potential megastructures when its light output showed irregular dimming patterns inconsistent with normal stellar variability or planetary transits. The star would dim by different amounts at unpredictable intervals, sometimes by more than 20%, far more than any planet could cause. Initial explanations ranging from comets to alien megastructures generated headlines, but subsequent observations found the star dims more in blue wavelengths than in red, indicating that dust rather than solid objects causes the dimming. A solid megastructure would dim all wavelengths equally. The mystery remains unsolved, but natural explanations appear most likely, with circumstellar dust clouds from recent comet disruptions providing the leading hypothesis. Biosignatures represent more conservative searches focusing on signs of life rather than intelligence. Atmospheric oxygen provides the clearest biosignature on Earth, because oxygen reacts readily with rocks and other materials, and maintaining high atmospheric concentrations requires continuous biological production through photosynthesis. Detecting oxygen in an exoplanet's atmosphere would strongly suggest life, though false positives exist. Photolysis of water vapor in atmospheres can produce oxygen through ultraviolet radiation, breaking water molecules apart, though this process typically remains limited unless the planet loses hydrogen to space rapidly. Ozone, methane combined with oxygen, and other disequilibrium atmospheric chemistries would strengthen the case for biology. The James Webb Space Telescope can analyze atmospheres of nearby Earth-sized exoplanets by measuring starlight filtered through the planet's atmosphere during transits. As the planet passes in front of its star from Earth's perspective, atoms and molecules in the atmosphere absorb specific wavelengths, creating absorption features in the spectrum. Different molecules absorb different wavelengths, allowing scientists to determine atmospheric composition by identifying which wavelengths get absorbed. JWST's infrared sensitivity makes it particularly good at detecting carbon dioxide, water vapor, and methane, key molecules for assessing habitability and potential biology. The nearest potentially habitable exoplanet, Proxima Centauri b, orbits the closest star at 4.24 light-years distance. This world contains at least 1.27 Earth masses and orbits its red dwarf star every 11.2 days, within the habitable zone where liquid water could exist on the surface. Red dwarf stars emit most energy in infrared wavelengths and burn much cooler than the Sun, so the habitable zone sits much closer. Proxima Centauri b orbits just 4.5 million miles from its star compared to Earth's 93 million miles from the Sun, but receives similar total energy. The proximity creates challenges including tidal locking, where one face permanently faces the star while the other faces eternal night, and increased exposure to stellar flares that could strip atmosphere and irradiate the surface with X-rays. TRAPPIST-1 provides another intriguing system containing 7 Earth-sized planets, 3 orbiting within the habitable zone around an ultra-cool red dwarf 40 light-years away. The system's compact nature puts all 7 planets closer to their star than Mercury orbits the Sun, completing orbits in 1.5 to 20 days. The planets likely experience tidal locking, and their proximity creates strong gravitational interactions causing orbital resonances. The middle planets in the habitable zone, TRAPPIST-1e, F, and G, receive energy similar to Venus, Earth, and Mars respectively. Density measurements suggest these worlds contain substantial water, possibly comprising up to 5% of their mass in some cases, compared to Earth's 0.5%. Such water worlds might feature deep global oceans hundreds of miles deep with high-pressure ice layers on their seafloors. Ocean worlds within our solar system provide immediate targets for astrobiological investigation. Jupiter's moon, Europa, contains a subsurface ocean beneath an icy crust, maintained in liquid state by tidal heating from Jupiter's gravity, kneading the moon's interior as it orbits. The ocean likely contains more water than all of Earth's oceans combined, reaching depths of 60 miles beneath ice 10 to 15 miles thick. Cracks in the ice suggest the ocean contacts the rocky seafloor, providing mineral chemistry and potential hydrothermal vents, where chemical energy could support microbial ecosystems similar to communities at Earth's deep ocean vents. NASA's Europa Clipper mission launching in 2024 will perform dozens of flybys, using radar to probe the ice thickness and analysing plumes of water vapour that occasionally erupt from surface cracks. Saturn's moon Enceladus confirmed an active subsurface ocean through geysers at its south pole that spray water hundreds of miles into space. The Cassini spacecraft flew through these plumes and analysed their composition, finding water vapour, ice grains, salts, silica particles, and organic molecules including methane. The plumes originate from fractures called tiger stripes, where tidal heating warms the ice enough to melt it. The ocean beneath sits perhaps 20 miles deep below 15 miles of ice. The silica particles indicate hot water at 200 degrees Fahrenheit, reacts with rock at the ocean floor, creating conditions favourable for certain forms of microbial life on Earth. Organic molecules suggest carbon chemistry occurs in the ocean, providing building blocks for potential biology. Titan, Saturn's largest moon, presents a completely different potentially habitable environment, with lakes and seas of liquid methane and ethane on its surface. This frigid world with temperatures of negative 290 degrees Fahrenheit features an active methane cycle, analogous to Earth's water cycle, with methane rain, rivers, lakes, and evaporation. The thick nitrogen-rich atmosphere creates hazy conditions that obscure the surface in visible light, but allow radar penetration. The Cassini-Huygens mission revealed a landscape with river valleys, lake beds, mountains, and dunes of frozen organic compounds. Beneath the surface, a water ocean likely exists 60 miles down, separated from the surface by an ice crust. Life adapted to liquid hydrocarbons instead of water represents speculative astrobiology, but the abundance of organic chemistry makes Titan compelling. Mars once contained surface water billions of years ago, when its atmosphere was thicker and warmer, and evidence includes valley networks carved by rivers, ancient lake beds with sedimentary deposits, and minerals that form only in the presence of liquid water. The water disappeared as Mars lost most of its atmosphere to space, likely due to solar wind stripping because Mars lacks a global magnetic field to protect the atmosphere. Water remains today as ice at the polar caps, as subsurface ice in mid-latitudes, and possibly as briny liquid water in underground aquifers. The discovery of potential underground lake systems detected by radar from the Mars Express orbiter remains controversial, but suggests liquid water might persist in isolated pockets, where salt concentrations lower the freezing point and geothermal heat provides warmth. Searching for past or present life on Mars drives current exploration efforts. The Perseverance rover collects rock samples from Jezero crater, site of an ancient river delta where water-carrying sediment entered a lake 3.5 billion years ago. The delta's layered rocks might contain fossils or chemical biomarkers from microbes that inhabited the ancient lake. Sample return missions planned for the 2030s will bring these rocks to Earth for laboratory analysis, with instruments far more sensitive than anything rovers can carry. Finding definitive evidence of past life would prove biology arises readily when conditions permit and would suggest life exists widely throughout the universe, wherever liquid water, organic chemistry, and energy sources coincide. Panspermia theories propose that life might transfer between planets or even between star systems, carried by meteorites ejected during impacts. Mars meteorites found on Earth prove that surface rocks can survive launch from Mars, travel through space for millions of years, and land intact on Earth without heating above temperatures that would sterilize any microbes sheltering inside. The Allen Hills meteorite from Antarctica, designated ALH 84001, contains carbonate minerals, organic molecules, and tiny structures that some scientists interpret as fossilized bacteria from Mars, though this interpretation remains highly controversial. Most scientists favor non-biological explanations for the structures and chemistry, but the possibility that we are all Martians descended from microbes carried here from Mars by meteorites billions of years ago cannot be ruled out completely. Interstellar panspermia faces greater challenges because spacecraft must survive enormous timescales, crossing the light years between stars while exposed to cosmic radiation that damages biological molecules. Calculations suggest that bacteria inside meter-sized rocks could potentially survive million-year journeys if shielded well enough. Stars occasionally pass within a few light years of each other during close encounters as they orbit through the galaxy, and material ejected from one system might reach another. The process remains speculative and difficult to test, but represents another pathway by which life might spread through space if it proves more difficult to originate than to transfer. The Drake equation estimates the number of detectable civilizations in the Milky Way by multiplying factors, including star formation rate, fraction of stars with planets, average number of habitable planets per star system, fraction where life emerges, fraction where intelligence evolves, fraction developing technology, and the typical civilization's lifetime measured against galaxy's age. Original estimates in 1961 suggested tens of thousands of civilizations might exist. Modern revisions using updated values from exoplanet discoveries remain speculative because we lack data on several factors, particularly the probability of life arising and intelligence emerging. The Fermi paradox asks why we detect no evidence of these civilizations if they exist in such numbers. Potential answers to the Fermi paradox span from optimistic to pessimistic. Perhaps civilizations commonly destroy themselves through warfare or environmental collapse shortly after developing technology, keeping their radio signatures detectable for only brief windows. Perhaps interstellar travel remains forever impractical due to physics we understand correctly, trapping civilizations in their home systems. Perhaps intelligence rarely develops technology capable of interstellar communication, with Earth representing unusual conditions that produced both intelligence and technological civilization. Perhaps life itself remains incredibly rare, with Earth representing the only inhabited world in the galaxy, or even the observable universe. The Great Filter concept proposes that some extremely difficult step in evolution from non-life to spacefaring civilization acts as a bottleneck preventing intelligent life from becoming common. If the filter lies in our past, between the origin of life and present day, then we should be optimistic because we have already passed it. The filter might be the origin of life itself, the development of eukaryotic cells, the evolution of complex multicellular organisms, or the emergence of intelligence. If the filter lies ahead of us, between present day and becoming a stable spacefaring civilization, then our future looks bleak, because most civilizations that reach our current stage fail to progress further. The filter might be nuclear war, climate catastrophe, artificial intelligence that destroys its creators, or some other disaster we have not yet imagined. Recent discussions focus on whether civilizations inevitably destroy their environments through technology and resource consumption, creating climate changes or pollution that make their worlds uninhabitable before they can expand to other planets. Earth's current trajectory toward climate disruption from fossil fuel combustion might represent a common pattern where intelligence develops during one stable climate, then destabilizes that climate through energy consumption before achieving the capability to leave the planet. This would explain the Fermi paradox if most civilizations collapse before becoming detectable across interstellar distances. Alternatively, civilizations might simply be quiet. The loud radio transmissions Earth produced during the 20th century might represent inefficient technology, quickly replaced by targeted communications like fiber optics and satellites that leak minimal radiation into space. Modern Earth produces weaker radio emissions than 1970s Earth, because cable and satellite replaced broadcast television, and we compress digital signals more efficiently. Extraterrestrial civilizations might follow similar paths, producing loud signatures for just a century or two before becoming undetectable. Combined with vast distances and light speed delays, this could explain why we hear silence. Perhaps intelligence proves rarer than we imagine. Evolution on Earth required 4 billion years to produce technological civilization, and the path involved numerous contingencies and apparent lucky breaks. Eukaryotic cells with nuclei emerged just once, through what appears to be an improbable merger of separate organisms that became the first cell containing mitochondria. Photosynthesis evolved in specific bacterial lineages and transferred to other organisms through endosymbiosis. Animals remained small and simple for millions of years before the Cambrian explosion of diversity 540 million years ago. The asteroid impact that killed dinosaurs created ecological niches that mammals filled, leading to primates and eventually humans. Remove any of these steps and Earth might still contain only microbial life. Intelligence itself provides unclear evolutionary advantages on the scales relevant to natural selection. Humans possess brains consuming 20% of our energy budget, while providing benefits that manifested only recently in evolutionary time. For millions of years, our ancestors survived as one primate among many without technology. The payoff came only in the last few thousand years, when cumulative culture and technology produced civilization. Many intelligent animals, including dolphins, crows, octopi, and elephants, demonstrate sophisticated cognition without developing anything resembling technology. Intelligence might be a rare accident that rarely reaches the threshold for civilization even when it emerges. Perhaps civilizations commonly transcend physical form, uploading consciousness into computers, or developing as artificial intelligences that have no interest in interstellar communication with biological beings. Such post-biological civilizations might be undetectable to searches focused on radio signals and physical megastructures. They might exist as software running on infrastructure so efficient it produces minimal heat signature, or they might migrate into virtual realities and ignore the physical universe beyond what minimum computational substrate they need. The possibility that we are alone remains scientifically valid given zero confirmed detections despite decades of searching. The conditions for life might be more restrictive than we realize, requiring not just water and chemistry, but specific combinations of planetary properties, stellar characteristics, galactic location, and timing in cosmic history. Earth might satisfy requirements we do not yet understand to be necessary. The universe might contain billions of planets without producing a single other instance of life. Or life might be common but intelligence incredibly rare. Or intelligence common but technological civilization almost impossible. Or perhaps the universe teems with life and the exponential growth of our detection capabilities over coming decades will reveal it. Each year brings more sensitive instruments, more comprehensive sky surveys, improved computer algorithms for analyzing data, and expanded search strategies including optical SETI, looking for laser pulses and searches for industrial waste heat. Future extremely large telescopes will directly image Earth-like exoplanets and measure their atmospheric spectra in detail. Gravitational wave detectors might detect signatures of cosmic string networks constructed by advanced civilizations manipulating space-time itself. The absence of evidence so far might simply reflect insufficient search depth rather than actual absence. The universe's habitability changes over cosmic time. The earliest billion years likely remain too hostile for life because first-generation stars contained only hydrogen and helium from the Big Bang, lacking carbon, oxygen, nitrogen, and other elements essential for complex chemistry. These elements formed inside massive stars and scattered through supernovae, enriching gas clouds that formed subsequent star generations. By the time Earth formed 4.6 billion years ago, the galaxy contained sufficient heavy elements. Future epochs will see star formation decline as galaxies exhaust their gas supplies. Red dwarf stars, which burn hydrogen incredibly slowly, will be the last stars forming and the last stars dying, potentially remaining active for trillions of years. Planets around red dwarfs might host the last civilizations in the universe, billions of years hence, when all other stars have burned out. Stellar evolution constrains habitability windows around different star types. Sun-like stars remain stable for roughly 10 billion years before expanding into red giants that incinerate their inner planets. Earth has perhaps 1 billion years remaining before the gradually brightening sun heats our world enough to boil the oceans and create a runaway greenhouse effect similar to Venus. Red dwarf stars remain stable for hundreds of billions to trillions of years, offering immense time for life to emerge and evolve, though their frequent stellar flares and tendency to roast planets during early active phases creates challenges. Blue giant stars burn so intensely they exhaust their fuel in millions of years, providing too brief a window for complex life to evolve on any orbiting worlds. Binary star systems, where two stars orbit each other, comprise more than half of all stars in the galaxy, and planets in such systems experience complicated climates as orbital dynamics shift planetary distance to one or both stars. Planets in close orbits around one star while the companion orbits farther away can remain stable and potentially habitable. Planets orbiting both stars in circumbinary orbits, like Tatooine from Star Wars, do exist, and some reside in habitable zones where water could stay liquid. The climate would vary dramatically depending on orbital configuration, as the planet experienced seasons driven by changing distances to both stars simultaneously. Globular clusters, ancient spherical collections of hundreds of thousands of stars born together, seem unlikely places for habitable planets because these clusters contain few heavy elements due to their age, having formed from primordial gas before many generations of supernovae enriched the galaxy's chemistry. Recent discoveries of exoplanets and globular clusters surprised astronomers and opened questions about whether life might arise even in metal-poor environments. The tightly packed stars in cluster cores, separated by just light days or light weeks instead of light years, would create dramatic night skies with hundreds of stars brighter than Venus visible simultaneously, and any civilization there would likely know about their stellar neighbours much earlier in their development than we learned about ours. Rogue planets drifting through interstellar space untethered to stars might offer another habitability niche if they retained thick hydrogen atmospheres providing greenhouse warming, and if they contained radioactive elements or had large moons creating tidal heating. Life in subsurface oceans on such worlds would never see stars, developing in eternal darkness and knowing nothing of the wider universe unless they developed technology capable of drilling through kilometers of ice to reach the surface. Such civilizations would face extraordinary challenges attempting space exploration from worlds with no nearby star to provide energy and no fixed reference point for navigation. The anthropic principle suggests we should not be surprised to find ourselves in a universe with properties allowing our existence, because observers can only arise in universes permitting their existence. This tautology provides limited explanatory power, but reminds us that selection effects influence what we observe. If the constants of physics were slightly different, atoms might not form, stars might not shine, or chemistry might not permit complexity. Though we inhabit one of the rare or perhaps unique configurations allowing consciousness to emerge and contemplate these questions. Whether infinite parallel universes exist with different physical constants, with ours merely one among countless variants where conditions permit observers, remains speculation beyond current science's reach. The simulation hypothesis proposes that we might live inside a computer simulation created by an advanced civilization, with all perceived reality being computed information rather than fundamental physical existence. Arguments supporting this idea note that if civilizations commonly develop the capability to simulate conscious beings within virtual worlds, and if they run many such simulations, then simulated consciousnesses would vastly outnumber original physical beings, making it statistically probable we are simulated. Arguments against include the question of what computational substrate the simulation runs on, and why the simulators would create such detailed and consistent physics. The hypothesis remains unfalsifiable, because any evidence against it could be programmed into the simulation. These speculations highlight how much remains unknown about existence itself, life's place in the cosmos, and the likelihood that other minds contemplate these questions from distant worlds. The universe appears vast and ancient and hostile across most of its volume, yet here we are, thinking beings emerged from matter following physical laws through chains of causation stretching back to the Big Bang. Whether this represents a common or rare outcome shapes how we view humanity's cosmic significance, and informs choices about preserving our civilization and expanding beyond Earth. The observable universe contains structure on scales beyond casual comprehension. Superclusters group together into even larger structures, forming the cosmic web's filaments. The Sloan Great Wall spans 1.37 billion light-years, making it one of the largest known structures. The Hercules Corona Borealis Great Wall extends perhaps 10 billion light-years. though measuring such enormous structures becomes difficult, and some astronomers dispute whether it qualifies as a coherent structure or merely a statistical fluctuation in galaxy distribution. These immense walls contain hundreds of thousands of galaxies arranged in sheet-like formations surrounding cosmic voids. The cosmological principle assumes the universe looks roughly the same in all directions when averaged over large enough scales, but finding structures billions of light-years across challenges this assumption, because such structures occupy significant fractions of the observable universe's diameter. If the universe contains structures 10 billion light-years across, and the observable universe spans 93 billion light-years, then these structures cannot be considered small-scale fluctuations. Some astronomers argue this indicates our understanding of structure formation remains incomplete. The universe's large-scale structure formed through gravitational instability, amplifying tiny density variations present shortly after the Big Bang. Quantum fluctuations during cosmic inflation created these initial variations, and gravity spent billions of years transforming them into the galaxy clusters and voids we observe. Computer simulations model this process by tracking how billions of particles interact gravitationally over cosmic time. The simulations match observations remarkably well, successfully predicting the cosmic web's basic structure, including filament sizes, void distributions, and cluster properties. However, simulations occasionally struggle with specific details. Satellite galaxies around the Milky Way and Andromeda appear more numerous in simulations than observations detect, creating the missing satellites problem. Dark matter simulations predict smooth halos around galaxies, but observations of galaxy rotation curves sometimes suggest lumpier distributions. Small discrepancies between simulated and observed galaxies' internal structure motivate debates about whether dark matter's properties differ from the standard cold dark matter model, or whether astrophysical processes involving gas, star formation, and feedback from supernova alter dark matter distributions in ways simulations do not fully capture. The history of the universe traces through several distinct epochs, beginning with the Planck epoch, lasting from time 0 to 10 to the minus 43 seconds when quantum gravity effects dominated and current physics breaks down. The Grand Unification epoch from 10 to the minus 43 to 10 to the minus 36 seconds saw 3 of the 4 fundamental forces unified into a single force. The electroweak epoch from 10 to the minus 36 to 10 to the minus 12 seconds witnessed the strong nuclear force separating from the electroweak force, and inflation occurred during this period, expanding the universe by at least 10 to the 26 times in perhaps 10 to the minus 35 seconds. The quark epoch from 10 to the minus 12 to 10 to the minus 6 seconds contained free quarks and gluons in plasma too hot for protons and neutrons to exist. The hadron epoch from 10 to the minus 6 seconds to 1 second saw quarks binding into protons and neutrons as the universe cooled below 10 trillion Kelvin. The lepton epoch from 1 second to 3 minutes featured electrons, positrons, and neutrinos as the dominant particles after most hadrons annihilated. Big Bang nucleosynthesis occurred between 3 and 20 minutes after the Big Bang, when temperatures dropped enough for protons and neutrons to fuse into deuterium, helium, and trace lithium. About 75% of normal matter became hydrogen, and 25% became helium by mass, with tiny amounts of other light elements. This composition matches observations of ancient gas clouds that have not been enriched by stellar processing, providing strong evidence supporting Big Bang cosmology. The photon epoch, or radiation-dominated era, lasted from 3 minutes to 380,000 years, when photons controlled the universe's energy density and expansion rate. Matter and radiation remained coupled with electrons scattering photons constantly, making the universe opaque like a dense fog. When the universe cooled to about 3000 Kelvin at 380,000 years, electrons could finally bind to protons forming neutral hydrogen atoms in an event called recombination. With free electrons removed, photons could travel without scattering, making the universe transparent for the first time. These photons comprise the cosmic microwave background radiation we observe today, cooled to 2.7 Kelvin by expansion. The Dark Ages followed recombination, and lasted until the first stars formed at 100 to 200 million years after the Big Bang. During this period, no stars existed to create light, and the universe's only illumination came from the fading glow of the cosmic microwave background red shifting into infrared wavelengths. Gravity pulled hydrogen and helium gas together into clumps that grew denser and hotter until the first stars ignited, forming from pure primordial gas containing no heavy elements. These first stars, called population 3 stars, likely achieved enormous masses of 100 to 1,000 solar masses because the absence of heavy elements prevented gas clouds from fragmenting into smaller clumps. The massive stars burned brilliantly but briefly, living just millions of years before exploding as supernovae that scattered the first heavy elements into space. The epoch of reionization began around 200 million years when ultraviolet radiation from the first stars and galaxies ionized the neutral hydrogen that filled space, separating electrons from protons once again. This process gradually transformed the universe from neutral to ionized over hundreds of millions of years as more stars formed and more radiation filled space. By 1 billion years after the Big Bang, reionization completed and the universe achieved a state similar to today, with ionized gas between galaxies, though much denser than current intergalactic medium, and galaxies forming at accelerating rates. The next several billion years saw the universe's peak star formation era, from roughly 2 to 6 billion years after the Big Bang, when star formation rates reached their maximum and galaxies built most of their stellar mass. Galaxies collided and merged frequently as the universe remained denser, and supermassive black holes grew rapidly at galactic centers, powering brilliant quasars. Some galaxies transformed from star-forming spirals into passive ellipticals as gas supplies exhausted or got heated by feedback from black holes and supernovae. The universe's appearance during this epoch bore little resemblance to today's cosmos, with more active galactic nuclei, more frequent supernova, and more chaotic galactic morphologies. From 6 billion years after the Big Bang to present, the universe entered the dark energy-dominated era where cosmic expansion began accelerating rather than decelerating. Star formation rates declined as galaxies exhausted their gas, and as expansion carried gas clouds too far apart to merge and form new galaxies. The universe evolved toward its current state with mature galaxies, depleted star formation, and accelerating expansion. Earth and the solar system formed 9.2 billion years after the Big Bang, arriving relatively late to cosmic history when the universe was already 2/3 its current age. The future epochs will see continued decline in star formation until it ceases completely in roughly 1 trillion years when galaxies exhaust all remaining gas. The stelliferous era, the current age of stars, will end, and the degenerate era will begin when the universe contains only stellar remnants, including white dwarfs, neutron stars, and black holes, with no active stars remaining. This era might last 10 to the 40 years until white dwarfs cool into black dwarfs, theoretical objects that have never existed because the universe remains too young for any white dwarf to cool completely. The black hole era beginning around 10 to the 40 years will feature black holes as the last significant structures, though even planets and stellar remnants will persist. Protons might decay with half-lives around 10 to the 36 years if certain grand unified theories prove correct, dissolving remaining matter into radiation. Black holes will evaporate through Hawking radiation over timescales, from 10 to the 64 years for stellar mass black holes to 10 to the 100 years for supermassive black holes. The dark era beginning around 10 to the 100 years will contain only photons, neutrinos, electrons, and positrons, spreading ever farther apart through endless expansion. These timescales exceed human comprehension by factors making the current 13.8 billion year age of the universe seem instantaneous by comparison. The universe has existed for roughly 1/1,000,000,000% of the time until the black hole era ends. Stars will shine for roughly 100,000 times longer than they have so far. The dark era will last essentially forever as far as any practical measurement cares. We live in the universe's beginning moments, in the brief flash when stars shine and galaxies cluster, before everything fades into cold, eternal expansion. Cosmic inflation theory proposes that the very early universe expanded faster than light for a fraction of a second, solving several problems in Big Bang cosmology. Before inflation, cosmologists wondered why the universe appeared so uniform in all directions, given that regions on opposite sides of the sky could never have communicated with each other because insufficient time had passed for light to cross between them. Inflation solves this horizon problem by proposing that the observable universe expanded from a tiny region small enough that all parts were in causal contact before inflation began. Inflation then stretched this tiny region to sizes vastly larger than light could have crossed since, freezing in the uniformity that we observe. Inflation also explains why space appears geometrically flat rather than curved into a sphere or saddle shape. Any initial curvature would be stretched by inflation until space appears flat, just as Earth's curved surface looks flat to observers standing on it, because we see only a tiny fraction of the total sphere. Measurements of the cosmic microwave background confirm the universe's large-scale geometry matches flatness to within 0.5% precision. The mechanism driving inflation remains unknown, though physicists propose scalar fields similar to the Higgs field underwent phase transitions that released enormous vacuum energy, creating exponential expansion. When inflation ended, this energy converted into matter and radiation that filled the universe and eventually formed atoms, molecules, stars, and galaxies. Quantum fluctuations in the inflaton field during inflation created the initial density variations that seeded all cosmic structure, making inflation responsible for everything from galaxy clusters to planets to life itself. If inflation occurred once, it likely occurred countless times, creating a multiverse where our observable universe represents just one bubble in an infinite foam of universes eternally inflating and producing new bubble universes. These other bubble universes would be forever beyond observation because they expand away from ours faster than light, and their interior conditions, including physical constants and particle properties, might differ from ours if different symmetry breaking occurred during their inflation. This eternal inflation scenario makes our universe's properties seem less fine-tuned because infinite universes with all possible properties exist, and we naturally find ourselves in one permitting observers. Critics note that eternal inflation and multiverse theories make few testable predictions and risk becoming metaphysics rather than physics. If other universes remain forever unobservable, how can we claim they exist scientifically? Proponents respond that inflation itself makes several predictions that have been confirmed, including flatness and the scale-invariant spectrum of density fluctuations in the cosmic microwave background. Eternal inflation follows as a mathematical consequence of the same physics that produces inflation in the first place. If inflation happened at all, eternal inflation likely happens too. The nature of time itself remains mysterious, despite seeming familiar. Time flows forward in human experience with past, present, and future arranged in order. But physics shows no fundamental reason for this arrow of time. The laws of physics work identically whether time flows forward or backward except for entropy, the measure of disorder which increases over time according to the second law of thermodynamics. This might explain time's direction because we perceive time flowing from low entropy, past toward high entropy future. But why the universe started in a low entropy state remains unexplained. The Big Bang's initial conditions were extraordinarily ordered compared to what random chance would produce, and this special beginning created the entropy gradient that defines time's arrow. Some cosmologists propose that the Big Bang was not the beginning, but a transition point in eternal cycles where the universe expands, contracts, bounces, and expands again infinitely. These cyclic cosmology models face challenges explaining how entropy resets during bounces, because thermodynamics suggests entropy must increase through any physical process. If the universe cycles eternally, entropy should approach maximum values, where all energy disperses uniformly and no structure exists. Models attempting to explain this invoke exotic physics during bounce transitions. The beginning of time itself poses philosophical problems. If the Big Bang represents time's beginning with nothing before it, what caused the Big Bang? Asking what happened before the Big Bang might be meaningless if time itself began at that moment, like asking what is north of the North Pole. Some quantum cosmology models propose that the universe tunneled into existence from quantum vacuum fluctuations, requiring no cause in the conventional sense. The Hartley-Hawking no-boundary proposal suggests the universe has no beginning in time if we treat time as a dimension equivalent to space near the Big Bang, forming a closed surface with no edge requiring causal explanation. These questions approach the limits of what physics can address because they concern conditions where quantum mechanics and gravity merge in ways current theories cannot fully describe. String theory, loop quantum gravity, and other approaches to quantum gravity might provide answers. but experimental tests remain far beyond current technology. We can probe energy scales up to tera-electron volts using particle colliders, but quantum gravity effects likely require energies near the Planck scale, at 10 to the 19 giga-electron volts, 15 orders of magnitude higher than what colliders achieve. Observing the very early universe through gravitational waves or other means might provide indirect evidence constraining quantum gravity theories. The universe's comprehensibility might be the most amazing fact of all. Human brains evolved to survive on African savanna, solving problems involving hunting, gathering, social cooperation, and avoiding predators. Yet these brains prove capable of understanding cosmology, quantum mechanics, and general relativity, uncovering laws governing scales from subatomic particles to the observable universe. Mathematics developed by humans successfully describes reality with remarkable precision, allowing predictions verified to 10 or more decimal places in cases like the electron's magnetic moment. Eugene Wigner called this the unreasonable effectiveness of mathematics in natural sciences, and why mathematics works so well at describing reality remains philosophically mysterious. Perhaps any universe permitting intelligent observers must possess regular mathematical structure, because intelligence requires predictable environments where agents can learn patterns and anticipate consequences. Chaotic universes with arbitrary rules would preclude evolution of intelligence, creating selection bias where only orderly universes get observed. Or perhaps humans perceive mathematical order because our brains evolved to find patterns even in randomness, and the apparent fit between mathematics and nature reflects how minds interpret experience rather than fundamental reality. These questions bridge physics, philosophy, and cognitive science without clear answers. The fact that we exist to ask these questions defies staggering odds if considered from first principles. Each atom in your body formed inside stars that exploded before the solar system existed. The carbon in your cells came from stars that lived and died billions of years ago. The calcium in your bones came from supernovae. The iron in your blood came from massive stars that collapsed, rebounded, and scattered their innards across space. You are literally made of stardust, and the atoms comprising your body will continue existing billions of years after you die, eventually recycling into future stars, planets, and maybe other living things. Your existence required Earth to form at the right distance from the Sun, with the right mass to hold atmosphere and water, the right composition to provide nutrients, the right planetary siblings to stabilize orbits and shield from excessive asteroid impacts, and the right moon to stabilize Earth's axial tilt and maintain stable climate over billions of years. The solar system needed to form in a spiral galaxy's habitable zone, far enough from the galactic center to avoid excessive radiation and close stellar encounters, but close enough that heavy element abundance permitted rocky planet formation. The universe needed to expand at just the right rate, neither collapsing immediately after the Big Bang nor expanding so fast that structures never formed. The fundamental constants needed precise values, permitting atoms, molecules, stars, and chemistry. Each step in evolution, from first self-replicating molecules, through prokaryotic cells, through eukaryotic cells, through multicellular organisms, through animals, through vertebrates, through mammals, through primates, through hominids, through humans, involve contingencies and survival of particular lineages through mass extinctions and environmental changes. Your ancestors survived countless challenges over 4 billion years of evolution, every one of your direct ancestors successfully reproducing before dying. The odds against your particular existence staggers belief, yet here you are reading these words, and the universe continues evolving, expanding, changing in ways that will reshape cosmic structure over coming billions of years. Galaxies will merge, stars will die, new stars will form until gas runs out, black holes will evaporate, and eventually nothing will remain but cold particles drifting through ever-expanding space. But for now, during this brief window of cosmic history when stars shine and planets orbit and life exists, we have the extraordinary privilege of observing, understanding, and contemplating the vast reality we inhabit. If you enjoyed learning these mind-boggling facts about the reality we inhabit, please hit that like button and subscribe to Space Reports for more explorations of the universe's strangest phenomena. Share this with someone who needs their perspective reshaped. Until next time, keep looking up and questioning everything you thought you knew about existence.